and welcome to NPTEL MOOC on Fiber Optic Communications Systems and Techniques course. Today is module 4 and we are going to look at further properties of uniform plane waves. Recall what we talked about, what we defined a uniform plane wave as. You had a wave which was propagating along x axis, it had an electric field E either along x axis or along the y axis. Both cases are different, but both cases can be independent. They are independent in the sense that you can have Ex, Hy and waves propagating along the z axis, or you have Ey and Hx and the wave is propagating along the z axis. We call this as uniform plane wave because as the wave propagates along the z axis, if you were to look at constant planes at some distance, so any constant plane z that you take, the electric field and magnetic field values will be completely independent of x and y, okay, which is the transverse plane, transverse to the direction of the propagation, and they only change along z value, right. Of course, they would also change along time, but at no point they are actually functions of x and y. Therefore, the electric field amplitude and magnetic field amplitudes would remain constant for a constant value of z. This is pictorially shown in this diagram, right. So, you can see here that I have drawn an axis which is along the z direction, and then I have erected lines indicating that these are constant values of electric field. Of course, if you take those constant planes such that the electric field value would be the same at these two planes, the distance between these two is called as the wavelength. In fact, when you write down a ray, remember light can also be thought about as a ray. This is what the picture that you actually have in mind, right. So, I have an interface like this, and then you have a ray of light incident at certain angle. Okay. What we actually mean is that the wave is propagating in the direction that I have indicated with this arrow, and the electric field and magnetic fields are constant, and these are the constant electric fields, and of course, there will be constant magnetic fields also transverse to this one. Okay. Such waves are called as uniform plane waves, and because we have a situation where electric field is transverse to magnetic field and electric field both are transverse. Transverse is a very fancy name for perpendicular. So, both electric field and magnetic fields are transverse to the direction of propagation. We have what is called as a transverse electromagnetic wave, and this is exactly what we are introduced to when we talk about light as a ray, but the electromagnetic nature means that there is electric field and magnetic fields, and in the case of a plane wave that we have considered, these two will also be further transverse to the direction of propagation. So, in terms of equations, you have x hat E0, E0 being the constant along x direction. So, let me modify this and write down this as E0x, and similarly I will write this as E0y. So far what I have said is that you have an electric field component either along x or along y. Can we have both at the same time? Yes, it is possible for us to have both non-zero at the same time. Okay. So, when they are non-zero at the same time, the total electric field would simply be the sum of the electric field along x and the electric field along y. So, where Ex is E naught x e power j omega t minus k 0 z, and where y is E 0 y e power j omega t minus k 0 z. So, please note that the value of k 0 and omega are not functions of x and y, they are not functions of the direction in which the electric field is propagating, okay, because this medium is what is called as a isotropic medium. So, for an isotropic medium, electric field and magnetic field, or the properties of the fields, do not depend on the direction in which the electric field and magnetic fields are oriented. Okay. So, if in a simpler case that I have an electric field which is entirely along the x direction, then I call this wave as x polarized wave. Polarization in this context means orientation. So, if I have electric field, take the first equation, in this equation there is no y term, and further if I assume that I am actually considering a case where k 0 z is equal to 0, then I have the electric field given by x hat E0 x being the amplitude of the x component, and then I have e power j omega t. Of course, in the real case this would be x hat E0 x cos omega t. Now, let me actually do something. I will write down two lines. This is the plane that I am considering, and the z axis would be coming out of this one, right. So, in the sense that I am actually looking towards the direction in which the wave is approaching me. So, the wave is approaching me and I am looking at this particular plane. So, one of them will be the x direction, this would be the y direction, and you know that if you go along from x to y, the direction should point towards z, right. So, if you just put them down like this and look at it from the top, you should have an x direction and a y direction, and x cross y should point in the direction along the wave, right. So, you have this coordinate system. Now, what am I trying to do here? I go back to the electric field E, which was basically E0 x, right. So, this was an x directed field, E0 x cos omega t. So, now let me try and write down where this electric field would be oriented at different times, and because of cosine nature, I am actually, it is actually easy to do, because I need to consider only 4 values for omega t to get a full picture, right. So, I mean 2 is also okay, but 4 seems to be a reasonable number. First, omega t is equal to 0. So, when omega t is equal to 0, cosine of 0 is 1, and the electric field will be directed entirely along the x axis with an amplitude of E0 x. So, this is what you actually obtain at omega t equal to 0. What will happen at omega t equal to pi by 2? At omega t equal to pi by 2, cosine is going through 0. So, the electric field will actually be 0, right, that is at omega t equal to pi by 2. Now, what will happen at omega t is equal to pi? Pi means cos of pi is minus 1. So, the electric field will be directed along minus x axis, right, with an amplitude of E0 x again, right. So, it will be directed along minus x axis at omega t is equal to pi, and at omega t is equal to 3 pi by 2, cosine is going through 0 again. So, you have the value, I mean the electric field having a value of 0 at omega t is equal to 3 pi by 2. So, what you have just seen is that no matter what time you consider, the electric field component would be oscillating along the x direction itself, right. So, the electric field is oscillating along the x direction itself. Naturally, if you repeat this problem by assuming that E0 x is 0, but E0 y is not 0, then you will see that the field is oscillating only along the y axis. So, you have an x axis alone oscillating or a y axis alone oscillating. Such oscillations along a particular line is called as linear polarization, and the wave is said to be linearly polarized along x or along y. How about this case where we consider the electric field to have both x component, okay. So, I have omega t minus, remember it is k0 z, plus y hat E0 y cos omega t minus k0 z, okay. So, you can show independently that Ex or the first equation will be solution of Maxwell's wave equation, the second one is independently the solution of Maxwell's equation. The sum of these two will also be the solution simply because of superposition, right. So, we have equations which are linear, and therefore, the sum is also a solution. Now, let us consider again the same kind of a scenario. I have omega t, I am going to consider k0 z is equal to 0. So, which means they are constants, and I am going to change the value of omega t. So, first let me assume omega t equal to 0. So, when I assume omega t equal to 0, what will happen to this expression? So, at omega t equal to 0, you have x hat E0 x plus y hat E0 y. If I have been given the values of E0 x and E0 y, then it is possible for me to use that values and then point out a vector at omega t equal to 0 in the direction given by this vector. Okay. So, this is the direction of the electric field, the total electric field at omega t equal to 0. For simplicity, let me assume E0 x equals E0 y equals 1, or rather 1 by root 2, for you will see why 1 by root 2 later on. So, you have this 1 by root 2. So, the direction of the electric field will be at a at an angle of 45 degrees as measured with respect to x axis. Okay. This would be the case at omega t equal to 0. What about omega t equal to pi by 2? In that case, the electric field will actually be 0, because cosine of pi by 2 will make this one go to 0. So, the electric field is at the origin, and at omega t equal to pi, the signs of EOX and EOY, or the direction of EOX and or the EX and EY will be reversed, which means that along the same line, but directed in the opposite direction, right. So, this would be the case at omega t equal to pi, and at 3 pi by 2, omega t equal to 3 pi by 2, the field would have gone back to 0. Now, what you have seen is that the wave is linearly polarized because it is oscillating along a line, but that direction or the angle at which this is oscillating is 45 degrees. In general, the direction or the angle at which this would be oscillating, a linearly polarized wave, would be at an angle of tan inverse of EOY by EOX, right. So, depending on the amplitude, your field component would be polarized in a line, but at an angle which is given by tan inverse of E0y by E0x. So, these are still linearly polarized wave except at an angle of theta. Now, let us do something else. It is possible for us to show that in addition to cosine type of solutions, even sine is a function of, sine of omega t minus k0 z is a solution of wave equation. And what is the difference between cosine and a sine? Cosine and a sine are different by a amount of phase which is equal to 90 degrees, right. So, one of them is a 90-degree phase shifted version of the other one. So, cosine and sine are 90-degree phase shifted. If I assume at some k0 z equal to 0, the electric field components are equal in amplitude, but have a cosine and a sine dependence with respect to omega t minus k0 z, then the total electric field would be 1 by root 2 x hat cosine omega t plus 1 by root 2 y hat sin omega t, as I have written here. Now, what is the polarization of this wave? Let us look at this. Again, I have x and y axis. Please remember, you are looking from the top and the wave is approaching you. Okay. So, this is the z axis, right. Z axis is coming out of this particular plane. At omega t equal to 0, what will be the situation? At omega t equal to 0, only the x component will be non-zero, whereas the y component will be 0, because sin 0 is 0. So, I have electric field directed along the x axis with a amplitude of 1 by root 2. Okay. Now, but omega t equal to pi by 2, the x component will be 0, the y component of the electric field will be along the y axis, of course, and it will also have an amplitude of 1 by root 2. Since between omega t equal to 0 to omega t equal to pi by 2, the field line has changed from x to y, right, and at omega t equal to pi, you will see that sine of pi will be 0, but cosine of pi will be minus 1. So, the direction of the electric field will be along minus x axis at omega t equal to pi, and at omega t equal to 3 pi by 2, this would be directed along minus y direction. So, what has actually happened is the electric field started off at omega t equal to 0 at lined up along the x axis, then it changed its position. So, you can put, for example, omega t equal to pi by 4 and realize that at omega t equal to pi by 4, the amplitude of this one would be 1 by root 2 along x axis plus 1 by root 2 along y axis. So, which means that in terms of magnitude or the length, they would actually be equal, right. So, if you now join all these tip, right. So, if you join the tip, you would see that the tip of the electric field vector is rotating, and in which direction is this tip rotating? It is rotating in the clockwise direction. So, if you now go clockwise direction and then look at your thumb, the thumb is pointing in the direction of the propagation. So, since you have used the right hand to get to the z axis, and this is a polarization, this is said to be right circularly polarized. Circular because at every point on this circle, the magnitude of the electric field, which is the value of that electric field at different values of time, will actually be constant, and because we have used a right hand right hand to point to the direction of the propagation, this is called as a right handed polarized wave, or simply called as right circularly polarized wave. Okay. Now, you can show, I will leave this as an exercise to you, what would be a left circularly polarized wave. Okay. So, left circularly polarized wave would actually start at omega t equal to say maybe along x axis, but at omega t equal to pi it would be directed along minus y. Therefore, you need to go with your left hand and point the left hand thumb along the direction of propagation, and then you would obtain left circularly polarized wave, and the equation for that one would be 1 by root 2 x hat cos omega t minus 1 by root 2 y hat sin omega t. Okay. In fact, we have a simple notation for all this polarization. We write the electric field as given the amplitudes E x and E y. So, instead of E 0 x, E 0 y, we will write this as E x and E y, okay, sorry, and call this as a 2-dimensional vector. So, this is a 2-dimensional vector E x and E y. So, this vector, which is a 2-dimensional vector, is called as a Jones vector, okay, and this is used to describe polarization of the electric field, and we note that E x and E y are themselves complex. Okay. We also have considered a situation where the magnitude of E square, which is given by E x square plus E y square, magnitude of course, would be equal to 1. This is just to normalize the intensity or normalize the power in electric field. We will talk about power sometime later, but this Jones vector is a very popular method for us to denote polarization. Okay. So, you can in fact write down, if you are not really happy with this one, you can write down this in a slightly different way. So, you can write this as E 0 x E 0 y e power j phi, where you can consider E 0 x to be real, E 0 y to be also real, and all the complex thing comes by having e power j phi. So, this phi is called as the phase difference. So, it is possible for you to even go and write something like this, and then the electric field would be given by E 0 x cosine omega t minus k 0 z, right, plus, and this of course would be along x axis, and then you have y axis field which is E 0 y cosine omega t minus k 0 z plus phi, and this phi controls what type of polarization we have. So, when phi is equal to 0, you have a linearly polarized wave, and when phi is equal to plus pi by 2 or minus pi by 2, you will have right circularly polarized wave or left circularly polarized wave. I am not sure which one is which one, it is just a simple algebra for you to figure this out. So, I will leave this as a exercise to you. You remember that we talked about some divergence in the last module, and we said that del dot E equal to 0. We could actually write this del dot E equal to 0, and we wrote this in the and we assume that this is the condition, and we expand it out in Cartesian coordinate system. What you have will be del E x by del x plus del E y by del y plus del E z by del z equal to 0. Clearly, in the case that we have been considering, there is no E z component, therefore, del E z by del z is equal to 0. Furthermore, because this is uniform plane wave, E x is not a function of x and E y is not a function of y, and this is also equal to 0. Okay. So, the conditions that we assumed are naturally satisfied. The condition for H will be del dot H equal to 0, but this is trivially satisfied because B is equal to mu naught H and del dot B is always equal to 0. Okay. And because of this particular case, I mean this is always true, and this B is equal to mu naught H in the free space condition, it trivially follows that del dot H is always equal to 0. So, to summarize, we have considered uniform plane waves which are characterized by having no E or H component along z direction, okay, which is the direction of propagation. Z is the direction of propagation. The wave propagates with a wave number k 0, wavelength of lambda, phase velocity V p given by omega by k 0, which is all properties of the medium itself. Of course, k 0 is also equal to omega times square root mu naught epsilon naught, and the velocity in this particular case for the free space medium is of course equal to c. Okay. You can look at all this, right, and then as I said, you can have E x non-zero and E y non-zero at the same time, and if you know what is the phase difference between the x and y components, you can have different type of wave polarizations. One is linear polarized and the other one is circular polarized. In circular you can have RCP and then you can have LCP standing for right hand circularly polarized and left hand circularly polarized wave. The other polarization that we did not discuss is elliptic polarization. In elliptic polarization what happens is that the field vectors rotate in the form of a ellipse. Okay. They have a certain minor axis and then they have a certain major axis. Okay. The tilt of this ellipse with respect to the x axis is given by the amplitude difference between the x and y, or the ratios of the amplitude between x and y, ratio of the amplitude of x and y components, and the angle phi, which is the phase difference between x and y components. And for simplicity case or for manipulation case, we introduced a Jones vector in which we simply assume that both x and y components are at the same frequency. Of course, this is a necessary condition, and that we can represent Ex and Ey in terms of their complex amplitudes and call this two dimensional vector as a Jones vector, which will tell us whether the wave is polarized in the linear direction or linearly polarized, circularly polarized, or elliptically polarized. Okay. Further, the nature of this uniform plane wave was such that as the wave was propagating along the z direction, the electric field was, if you assume it to be along the x direction, then the magnetic field will be along the y direction, because then E cross H would point along z. Incidentally, I will not derive it here, but we can define what is called as a Poynting vector density, okay, or sometimes called as Poynting vector itself, or sometimes also called as power density vector, which is given by S equals E cross H. Okay. If you use the full electric field in the real form, magnetic field in the real form, then this S corresponds to the power density of the wave that is being propagated along the z axis. So, you can use full electric field E in the real and H form, but if you were to use the complex form that we discussed, okay, or the time harmonic form as we call it, where the time dependence is always e power j omega t, then the equation that you can write in that particular case will be slightly different. You can actually write the Poynting vector as half real part of E cross H, half of E cross H star. This half is just for normalization purposes, and this S is the Poynting vector which tells you how much is the power density being carried away, right. Of course, the power itself is obtained by integrating over the area, and in this case the area will be along x and y direction. So, this would be S dot ds, where ds is the surface element given by z hat dx dy, right. So, you hope I hope that you remember this surface density or the surface integral concept, and whatever the surface that you consider which has certain bounds along, say, x equal to 0 to x equal to a, y equal to 0 to y equal to b, over this surface if you know what is the S vector, right, which is the Poynting vector, then you can integrate over that limit and obtain what is the time average power that is being carried by this particular wave. So, this is the time average power. If you simply write E cross H, that is called as the instantaneous Poynting vector, but most of the times we are not interested in the instantaneous power, because these are oscillating at terahertz, and I really do not have a detector which can follow those instantaneous variations. So, I am mostly interested in the average powers. So, and in that particular case the time average power is given by half E cross H star, where E and H are represented by their complex forms. That is, we do not have e power j omega t in that kind of a thing is already assumed implicit. Okay. So, the time harmonic form or the complex form or the phasor form, they all are essentially the same, just the names are different. The fundamental idea is the same. The time dependence is dropped out, assuming e power j omega t. So, this was all about Poynting vector, and previously we have seen Jones vector. Then to describe polarization, we have another vector called as Stokes vector, which I will not describe it now, but we will postpone the discussion of Stokes vector when we want to discuss polarization of the wave that is propagating inside the fiber. Okay. So, we will postpone that discussion later on, and for now just recap that plane waves that we considered were characterized by waves propagating along z direction, no E and H component along z direction as well. We had defined a few of the parameters such as wave vector or the wave number, wavelength, and we described the phase velocity. More of this will be talked about in the next modules, but let me ask you one thing. So, is it possible for the wave to propagate in any other direction apart from z? It is possible. For example, if the wave is propagating in the x and y plane, right, or in the x and z plane making an angle of certain theta with respect to x axis, then the direction of the propagation will not be purely along z hat or along x hat. It would be in the direction of the vector, the unit vector, along whatever the direction that the wave is propagating. In that case, electric field will not be purely in the x and y directions, because remember, if we are considering transverse electromagnetic waves, then the electric field has to be perpendicular to x axis, perpendicular to the direction in which the wave is propagating. So, if the wave is propagating along z axis, electric field could be along the x axis and magnetic field could be along the y axis, right. But if we turn around and then say that the direction of the wave propagating in free space is at a certain angle with respect to the z axis, then clearly electric field will also be now having two components. It will have a component along x and it will have a component along z, right. Similarly, magnetic field will also have a component along x and or rather y and the corresponding z component. So, this type of a wave is called as obliquely travelling wave, oblique in the sense that it is not directed along z axis, but also remember our x, y, z coordinate systems need not be the same coordinate system for the wave also. For example, it is possible for us to define the z axis as the direction of the wave propagation, then x axis as the electric field and y axis as the magnetic field. But if we fix the coordinate system first and then we find that the electric field or the wave is propagating at a different angle, then we should be ready to consider the components of that direction vector. In that case, instead of wave number, we talk about wave vector, that is k itself will become a wave vector. Okay. And in that case, the direction of propagation of the wave will be given by the dot product, or rather the direction of the wave propagation will be denoted by k, and this k itself will be a vector, and the corresponding spatial part will be given by k dot r, and the electric field direction will also be determined by what is the direction of this k vector. So, what it means is that k can be k0 x x hat plus say k0 z z hat. In the previous case, we had considered only that the wave k will be directed along the z axis, right. In this case, I am considering the k vector to be along both axis, in the direction which is at a certain angle with respect to z axis, having values along x and having a value of along z. So, in this case, it is not purely propagating along the z axis, but it is propagating at a certain angle which is given by tan inverse of k0 x by k0 z. Okay. And the electric field itself will be given by the electric field, which is now a function of r and t, is given by its vector, which is dependent on this direction. So, the electric field could be this way directed, this is the electric field direction, and then in terms of the phase it would be k dot r. Of course, in this case r is equal to x x hat plus y y hat, and you will see that k dot r will turn out to be k0 x x plus k0 z z, indicating that wave is propagating in the x and z planes. So, we stop here in this module, and in the next module consider what happens when a wave which is propagating in free space goes and hits a medium, right. Thank you very much.